In the previous video, we looked at the length of some complex shapes. In this video, we're tackling coordinate geometry. We're going to be converting geometry problems into algebra problems. A tricky geometry problem becomes extremely straightforward and easy with coordinates. Let's explore how to do this. Starting with the basics, I'm sure you guys all know the equation of a line, slope-intercept form, the slope formula, the distance between 2 points. Now here's something that's also cool, which you might not know. If you have a line, its slope is also equal to the tangent of this angle. This angle, find the tangent, that's equal to the slope as well. So cool thing to keep in mind, but we'll talk about more about trig in later videos. And another thing that you may not be familiar with, the distance between a point and a line is given by this complicated looking formula, but it's really not that complicated, don't worry. So let's say we have an equation y equals 3x plus 5, right? So the first step to finding the distance, let's say we're trying to find the distance between this point and 2 comma 5, let's say. The first step to finding distance, convert your equation to standard form, and specifically ax plus by plus c equals 0. So 3x minus y plus 5 equals 0. So now, there's a few very important things here. What you're going to want to do is, it's actually quite simple. You just take this equation that you have here, 3x minus y plus 5 equals 0, and you plug in your point, 2 comma 5. So 3 times 2 minus 5 plus 5, right? Y is 5, x is 2. So we have that. And now what do we divide this by? Be very careful here. In our equation, now be very careful here. We're not looking at our point here. We're looking at the equation. What we do is we find the sum of the square root of the sum of the squares of these two values. So the square root of 3 squared plus 1 squared, or negative 1 squared, which is the same thing. Again, remember, we're not doing anything with this point here. We're not doing the square root of 2 squared plus 5 squared. We're doing the square root of these coefficient of x and the coefficient of y. That's often the most common error when doing this point-to-line formula thing. So 6 over root 10 is our distance, which is approximately 2-ish, which makes sense given our conditions. Okay, let's move on to the equation of a circle. Let's say it has center a comma b and radius r. This is the equation. You're probably familiar with this. So now let's jump straight to examples, how this is actually applied. Let points a equals 0 comma 0, b equals 1 comma 2, c equals 3 comma 3, and d equals 4 comma 0. A quadrilateral, this quadrilateral we have over here, it's cut by a line. And basically when we draw this line, also another thing that I think is missing from here, I'm not sure why, I'll add it later, is the Shoelace formula for finding the area of any polygon really when you have its coordinates. So for the sake of simplicity, let's just take a triangle. Of course, anything will work. So let's say we have 1, 2, 2, 3, let's say 3, 5, and then let's say 2, negative 1, something like this. So we just took 4 points. So the first step is to find the order of the points. If you're dealing with 3 points, this doesn't matter. But if you have 4 or more points, the points have to be in the order they're connected in. Otherwise, you'll get a faulty area. So 1, 2, 2, 3, and you don't have to graph these precisely, just get a rough idea. Enough to the point where you can find the order of the points they're connected in to form this quadrilateral. In this case, the order is 1, 2, then 2, negative 1. So basically, we just gotta move this here. Then 2, negative 1, then 3, 5, and then 2, 3. And that would form this quadrilateral. which we're trying to find the area of. So we have to put them in any order, really. It doesn't matter whether it's clockwise or counterclockwise. What we can't just go is say this point, then this point, then this point, then this point. No. For a triangle, it doesn't matter because no matter which direction you go in, you're going to draw the triangle. Okay, so now we've had our points, write them all out in order. And now this is like where the shoelace kind of parts kicks in. So what we're going to do is we're going to first multiply these two numbers, then multiply these two numbers, then these two numbers, and then these two numbers at the end. So 1 times -1 plus 2 times 3 plus 2 times 5 plus 3 times 2. -1 plus 6 plus 10 plus 6, that is 21. Now that's kind of our first sum, let's call it, right? So let's just call it, it's our first value. So now what we're going to do is we're going to go the other way, like this. Now we just go the other way and we do the same exact thing. 2 times 2 plus 2 times -1 plus 3 times 3 plus 5 times 1. That is 4 plus -2 plus 9 plus 5. That is 16. So now what we do is we take both of these sums and we find the magnitude of the difference. So if it's negative, you just make it positive. And then just subtract the smaller one from the larger one, basically. In this case, 21 minus 16, that's 5. Okay, so now with our difference, all we do is we divide it by 2. And that's our area. Cool formula. And in this case, you can also do a quick sanity check. In this case, 5/2 seems reasonable because of the fact that, roughly you can estimate it using like a rectangle or something. It seems roughly about right. So, you didn't make any obvious errors by our sanity check. Okay. Now, let's tackle this problem which actually uses the shoelace theorem. So we have a line drawn. It intersects CD at this point, and we want to find the point such that this area is equal to this area, splitting right through the halfway point of the area. And you might notice AD, well, this is 0, 0. This is 4, 0. AD is 4. So, if we can find out what this area must be, then we can easily find out what the height is. And if we find out the height, then it should not be too hard to find out what this coordinate here is. So really, we want to find out what this area should be. But because of the fact that this area is equal to this area, and it's therefore exactly half of the total area, all we do is first find the area of this quadrilateral. And to do that, we have our handy shoelace theorem. 1, 2, 3, 3, 4, 0. We write them all out in a line, just like that. And then after, we just do our kind of, connecting line. So this, 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 and this. And if it's 0, don't worry. Just 0 times 2, plus 1 times 3, plus 3 times 0, plus 4 times 0. There's a lot of zeros here, so this is nice and easy on our part. Just 3. Okay, now we go the other way. Erase these purple lines and draw blue ones instead. So, this way, this way, this way, and this way. The blue, 0 times 1 plus 2 times 3 plus 3 times 4 plus 0 times 0. That is 18. So, the difference between these two, 15. Our area, 15/2. So the area of this thingy is going to be 15/4, triangle AED. And area is half times base times height. So half times base times height, this is equal to 15/2. Well, that means the height is just 15 over 4. This thingy, 15 over 4. In order for the area to be, but the area should be 15 over 4 because the area of the quadrilateral is 15 over 2, so the area of this triangle has to be half of that. Sorry, my bad. Then this thing will actually have to be 15 over 8 in order for the area to be 15 over 4, because 15 over 8 times 1/2 times 4. So this is 15 over 8, actually. Oops, for that. So 15 over 8 and 4 is the base AD. How do we find the point E, the coordinates? Well, we know the coordinates of D is 4, 0. And we know this is going to have a y coordinate, therefore, of 15 over 8. Because it's 15 over 8 above. But the question is, what is going to be its x coordinate? How do we do that? Similar triangles, or really you don't even need similar triangles. You can just use the equation of a line. This is 3, 3. So, I mean, you can write here's like kind of the slow way. Well, if you can do it, it works just fine, but I think it's a little bit boring. You find the equation of this line, y equals blah, 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 x plus something, something, whatever. And then you just plug in y, and then you solve for x. But here's kind of like a fancy trick you can do here, which I'll show you. This over here, 0 to 15 over 8 to 24 over 8. It goes up 15 over 24th of the way. This is, in total, goes up 3, and this goes up 15 over 8. So in total, it goes up 15 over 24th of the way. So therefore, it's also going to go up 15 over 24th of the way in terms of the x coordinates. So what does that mean? Well, in total, this drops by 1 in terms of x coordinates. And so basically, because we're going up 15 over 24th of the way, we subtract 15 over 24, which is, let's simplify, minus 5/8. We're going to subtract 5/8 to our x coordinate. And that leaves us with just 27 over 8. So therefore, our answer, well, our coordinate is just going to be 27 over 8, comma, 15 over 8 by our logic. And again, you can write the equation of a line. You're going to get the exact same thing. It's a little bit more, this is a little bit more of a nice argument, really. Okay, so now, I mean, it's pretty simple from here. We can do addition. 27 plus 15 plus 8 plus 8. 27 plus 15 plus 8 plus 8 is, well, 27 plus 15 is 42 plus 8 plus 8. That's 58. So our answer is 58 for this problem. The key idea, well, this was not a very difficult problem. The key idea was just use shoelace, then use half base times height in order to find what the height of the thing would be. And then once you found out what the height is, you use this equation of a line or this going up trick in order to find the x coordinate. Okay, and let's try another problem. You definitely did not see the answer. Don't worry about that. A triangle with sides 5, 12, 13 has both an inscribed and circumscribed circle. What is the distance between the centers of these circles? The first thing, this is kind of like a combination, right? Directly using coordinate geometry is going to be a bit tricky, but using some facts you know about geometry along with some coordinate stuff makes for a very nice and simple solution. Okay, so naturally, you want to find distance. It's a really good sign to use coordinates. Another good sign to use coordinates, right angles, parallel lines. Because they're easy to deal with coordinates. If you've got a bunch of diagonals, it's not a great idea to use coordinates. We've got some random triangle here. Not a great idea to use coordinates. Unless you're already given it, of course. Okay, so naturally, we want to find the distance between the incenter and circumcenter. Let's just find each of the coordinates. And for this problem, we kind of have to define our own coordinate system. So the simplest thing, let's let this point be the origin. Let's let this point be 12, 0. Let this point be 0, 5. Now, if you remember from geometry, the center of a circumcircle is just the midpoint of the hypotenuse. And by coordinates, we got that this is 6, 5 halves. Okay, now what is the coordinates of the incircle? Of the incenter, sorry. How do we do that? This is a little bit more tricky, but it's not that bad. We've got a circle here, let's draw it. And this is a really good property for, I know it's such a great circle right now. So we draw our radii, R. When you have right triangles, incircles are really, really nice. So if you look over here, this is 90, 90, and 90. So this is also 90. And that means this is a square. So this coordinate is just R, R. So we find what R is and we're done. But we know how to find the in radius of a triangle. Area by semi-perimeter. The area, half, base, height, 30. The semi-perimeter, half times 5 plus 12 plus 13. Which is half of 30, 15. The area over the semi-perimeter is 2, so R is 2. So this point in radius just has coordinates 2, 2. And now we just use our distance formula. The square root of 4 squared plus 1/2 squared. That is the square root of 16 plus 1/4. Or the square root of 65 over 4, which is just root 65 by 2, and that's the answer. Another cool problem, key idea, notice that the circumcenter is just the midpoint of the hypotenuse, and to get the midpoint of 2 points, we just have to average those 2 points. That's another cool thing to remember. And to get the coordinates of the incenter, all we have to do is find the in radius, and then notice by our cool properties, it's R, R. This is kind of like a good example of hybrid. You know, we use some geometry and we use some algebra, and it gave for a really nice solution. Okay, now let's check out another problem where we kind of have to impose our own coordinate system here. In rectangle ABCD, AB is 6, BC is 3. Point E is between B and C. Point F is between E and C, such that BE, EF, FC. Basically, each of these 3 things are 1 because BC in total is 3. Segments AE and AF intersect BD at points P and Q. We're asked to find this ratio of length. So naturally, we want to deal with coordinates here because we have a rectangle, and rectangles are super easy to deal with coordinates. Let's just make DC the x-axis and AD the y-axis and D the origin, because we can make whatever coordinate system we want. And this is going to be 6, 0, then 6, 3, and then 0, 3, right? Because this is 6 and this is 3. So now, and let's just find the coordinates of F and E as well, which we can do because we know 1, 1, 1. So now, all we have to do is, using equations of lines, we can find out the points P and Q. We find the equation of the line, of this line, we find the equation of this line, and then we find the equation of this line. And then we just use coordinates to finish. Okay, so let's do this. Let's first find the equation of... Let's find the equation of this line first. Why not? And this is pretty simple. I'm just going to color code this. So this line is just y equals half x. Because 0, 0, and then 3, 6. So in both cases, the y value is half of the x value. Okay, now let's move on to some more cool lines, some more complicated lines. This purple one. Okay. So this one, it's a little bit more tricky. We find the slope, which is 3 minus 1 over 0 minus 6, which is negative 1/3. And then now we just use our equation of a line. Y equals negative 1/3 x plus 3. We can double check in the second point. Yes, it does indeed work. Okay. Now for the final one, final line. See how kind of the general theme here is we use coordinates to convert these types of geometry problems into simple algebra problems, which is kind of the main idea here. And this one, we do something very similar. The slope is 2 minus 0 over 2 minus 0 over, or sorry, not 2 minus 0. Okay, 3 minus 2 over 0 minus 6, negative 1/6. So our equation is just minus 1/6 x plus 3. And now we just do algebra. We find the intersection of the green line and the blue line first. That's P. So P, we just solve this equation and this equation. We set them equal. We get the coordinates of P, we just set those equations equal. We get half x equals minus 1/6 x plus 3. We add 1/6 x to both sides. We get 2/3 x is 3, where x is 9/2. So there's actually a neat little trick I'm going to do here. The x coordinate is 9/2, and you can find the y coordinate, but I'm just not going to for now because I don't need to. Now finally, we just find the coordinates of q, which is a very similar standard process. Intersection of purple line and blue line. And oh, it looks like this point I found was actually q. This point was q actually, because we had half x equals minus 1/6 x. Oh, never mind. Yeah, okay. This was P. I had it right originally. And then Q is the intersection of the blue line and the purple line. So the blue line, that's just half x equal to minus 1/3 x plus 3. So 5/6 x equals 3. X equals 6/5 times 3, 18 over 5. So Q 18 over 5, and I'm not going to find the y coordinate, and you'll see why in a second. So now one way of finishing this is to find the y coordinates of P and Q, and then use a distance formula using this, this, and this. But that's long. We're always looking for the smart solutions here. Let's take a look at the smart solutions here. So let's drop all the altitudes from P. The ratio of this length to this length to this length is just going to be equal to the ratio of this length to this length to this length. Why? Similar triangles. Just because the ratio of this to this equals the ratio of this to this equals the ratio of this to this by similar triangles. And from there, we get that this to this to this is just this to this to this. So we can also draw subtriangles here if that helps you see why. These are all similar, so this to this equals this to this equals this to this. So in other words, we just need to find the ratio of these x coordinates. We don't even care about the y coordinates. And let's just add d here, 0 comma something, and b here, which is just 6 comma something. We don't care what it is. So now let's just find the ratio BP to, or I'm just going to switch these orders really quickly to make it in order of the problem statement. It's the same thing, really. I'm not changing anything. So now let's just find BP. Well, 6 minus 9/2, that is 3/2. 9/2 minus 18 over 5. Well, 9/2 is just 45 over 10. 18 over 5 is 36 over 10. 9/10. And then 18 over 5 is just 18 over 5. We multiply by 10 to this whole ratio. We get 15 to 9 to 36. We can divide by 3. 5 to 3 to 12. So our answer is just going to be 20. Because 5 plus 3 plus 12 is 20. So great problem in coordinate geometry. The main idea was it's pretty straightforward, really, if you think about it. I mean, you assign coordinates, you find equations of lines, and then you solve equations. And the key idea at the end, the smart part about this problem, is rather than finding these ratios, you could consider similar triangles and realize that this to this is equal to this is equal to this. So it suffices just to find these x-coordinate ratios instead. And now let's move on to this problem over here. In right triangle ACE, we have AC is 12, CE is 16, and EA is 20. We have points B, D, and F located, so that AB is 3, and by subtracting we get BC is 9. We have CD is 4, and by subtracting we get DE is 12. And EF is 5, and by subtracting we get AF is 15. What's the ratio of DBF to ACE? Now if you know trig, there's a pretty simple solution using 1/2 AB sine C, but let's solve it the coordinate geometry way. And because we have a right triangle, this is like the key words that should make you jump and be like, okay, right triangle, all points to find, coordinate geometry is going to be the way to go. So naturally, the easiest thing to do is let this be the origin. Now you might be like, do you have to set it to the origin? No. Why are we setting it to the origin? Ease of calculation. Like we saw earlier, having the origin just made things so much easier because we just use this pretty simply. But you can really use anything you want. I recommend the origin for your right angle point. Now we get 0, 9, 0, 12, 4, 0, 16, 0, and then this is also not that difficult because, like the logic I mentioned earlier, this is 3/4 of the way down from A. So we just say, okay, our increase in x coordinate is 16. So we're going 3/4 of the way from 0 to 16, which is 12. And then similarly for the y coordinate, we're going 3/4 of the way down from 12. So we go all the way till 3. 3/4 of the way down from 12 to 0. So 12, 3 is F. Okay, so ratio of area DBF to ACE. DBF, we can find that using Shoelace theorem, the area. And ACE, well, that's just a right triangle with sides 12 and with legs 12 and 16. So 1/2, 12, 16, 96. Now we could do Shoelace, but that's not needed. There's a much simpler way using just half times base times height. And now for BDF, let's now use Shoelace theorem, our favorite theorem. So because we're dealing with only 3 points, our order of points does not matter. And now we just use our standard, this method, 0, 0, 4, 3, 12, 9. You kind of see the advantage of using 0 here. I mean, a lot of points are just 0. Just nice to make things faster and easier for us. So that's 108 plus 12, 120. And then now let's erase these red lines. Okay. So then now we have this, and this. 9 times 4. 9 times 4 plus 0 times 12 plus 3 times 0, which is just 36. And now to find this area, we do 120 minus 36. Divide all of that by 2. And this will just give us 84 by 2, which is 42. And the ratio of areas, 42 to 96. You can simplify that out. Divide by 6. 7/16 is the answer for this problem. The key idea here, really just let the right angle be the origin. Find these points using standard coordinate methods. And this one, we did the trick of going 3/4 down. And then just Shoelace and right angle formula allowed us to finish pretty simply. Finally, for the last problem, this is the hardest problem of today. Let ABCD be a square with side length 8. let M be the midpoint of VC. Okay, let's draw this diagram out. We got a square A, B, C, D with side A. M is the midpoint. And W be the circle passing through D. So now we've got circles involved. This is why this problem is more tricky than the previous ones. The previous problems we were just dealing with, lines really. Now we've got some more complicated geometric shapes in the mix. So we're gonna have to use the equation of a circle in this problem. Okay, so we have M be the midpoint and W is the circle, or omega is the precise name for that symbol. We have a point here. These are the radii. We will always want to draw the radii. But in this case, we're doing coordinates, so it won't really matter. In general, you should draw the radii. So it's just good, get in a good habit of doing it. Because if you're solving this problem by not using coordinates, then you would need the radii to be drawn. Okay, so O is this point here. X be the intersection of W with AB, so this is X. And Y with OX with AM. So we're intersecting AM. Why is it so thick? AM with OX. And that's Y. And we're asked to find OY. So what we're going to do to this problem is very similar. We're just going to assign coordinates. So let's say 0, 0, 8, 0, 8, 8, and 0, 8. Okay. So now we have a circle. We want to find the equation of this circle, first of all, right? In order to find the equation of the circle, we need the center and the radius. How do we find the center of the circle, first of all? Well, this is R. This is R. This is R. Let's just, yeah. So the key thing here is that the side length is 8. So this thing is going to be 4. And that means this distance over here, we can form a right triangle just like that. So now take a look. This distance plus this distance equals 8. This distance over here is just square root of R squared minus 16 by the Pythagorean theorem. And that distance is R. We have this plus R, and this in total is 8. So from here, we can pretty easily solve for R. And the trick is, in this case, you want to isolate the square root term. So we do that, and now we just square both sides. And it's going to be a pretty simple equation to solve. So R squared cancel. We're left with 16R is 48, or just R equals 3. Now R is 3. Now we know that for sure. Wait, I think we did something wrong here. R is not 3. So we have square root of R squared minus 16 equals 8 minus R. We squared both sides. And then we got that. Oh, this is 80. We added 16 to both sides, right? So we got 80 on the right-hand side and then 16R on this side. So R is 5, not 3. So then this point over here, well, M is just 8, 4. And then we're going to go 5 left. So 3, 4. So our center is 3, 4, and our radius is 5. And now we can just write the equation of the circle. X minus 3 squared plus y minus 4 squared equals 25. Because the radius is 5. And now we want to find x. Well, we want to intersect the circle with this line. Well, this line has just an equation of y equals 8. So we just plug in y equals 8 over here. Because we want to intersect it in order to find the x coordinate. So we get x minus 3 squared plus 16, 8 minus 4 all squared is 16, is 25. And that means x minus 3 squared is 9. So x minus 3 is either 3 or negative 3. So x is either 0 or 6. Those are the two intersection points. But take a look. X equals 0 is a. So that's going to be, it says besides a. So therefore, we're going to have x equals 6. This is going to be 6, 8. Cool. Okay, so now all we have to do, find the equation of this line, and solve to get this point. That's simple. Okay, so starting off with this, the purple line. The equation of this line is just y equals 2, or y equals 4/3 x. Because the slope is 8 minus 4, which is 4, divided by 6 minus 3, which is 3. So the slope is 4/3, and then 4/3 times 3 is 4, so plus 0. Okay, now what about this orange line? Well, this is also pretty simple. The slope is 8 minus 4 over 0 minus 8 minus 1 half. And then it's just going to be y equals minus 1 half x plus 8 then. So now all we have to do is solve this systems of equation. One variable, super easy. 4/3 x equals minus 1 half x plus 8. Let's add half x to both sides. We get 8/6x plus 3/6x is 8. So x is 6 over 11 times 8, 48 over 11. So x is 48 over 11. And then y is 4/3 of that, 64 over 11. Now, we want to find the distance between O and this point, which is y. What do? Distance formula. So let's just rewrite this, 3 and 4, as 33 over 11 and 44 over 11. So we can do our distance formula. Now, distance formula, 15 over 11 squared plus 20 over 11 squared. Okay, so now, what is this? Well, we can just use, we can do this manually, or we can notice that 15, 20, 25 is a Pythag triple. This is just, you can factor 11 from the bottom. And 15, 20, 25 is a Pythag triple, so this is just 25 over 11. So 25 over 11 is the answer to this problem. Cool problem. The main idea, you want to find the equation of a circle. And be careful about finding the equation of a circle, as it can get messy quickly. In this case, it was a good idea because we just had a line and a circle. But if you have multiple circles, it's possible to solve them, but it can get very hard. So I would be cautious when you're going to use coordinate geometry. And some caution things that you keep in mind, like I mentioned, too many circles, slanted lines. You don't want to be trying to use coordinates when you have this really ugly, and then you have got a bunch of lines. Coordinate geometry is useful, but don't overuse it. Make sure you know right angles, parallel lines, all those good things for using coordinate geometry. In this problem, we just had to find the equation of a circle, and then it was just simple algebra. And also we had to use this logic of r squared minus 16 plus r equals 8, using some Pythag theorem stuff. So we kind of combined coordinate geometry and normal geometry as well into this one solution. Thank you for watching this video. By the way, for the next video, you can check out the advanced topics where we'll talk about the floor and ceiling function. If you're interested, these are more for the late AMC problems, but it's still good to know. You can check out that video right over there.